Hello everyone. This is the start of materials for exam 3, starting with operational amplifiers. So this is not part of your second exam. Operational amplifiers, or op-amp, are active devices. They are made of transistors, resistors, capacitors, and they are very important, one of the most commonly used integrated circuits in electrical engineering. If you look at the internal circuitry of this operational amplifier, you would probably guess that you're not going to study that. This is very senior level electrical engineering material. But what I want you to see here in this figure is 3 red dots. 2 of them are inputs called non-inverting and inverting inputs, and 1 here output, okay? And we don't care about the rest of this. So as simple as that. Also, this is not exactly required for your exam or anything, but if you look at the voltage, the top rail voltage, which is V plus or V positive, and the one at the bottom, which is V negative, these are called supply voltages. And in your mini lab that you're going to do on Wednesday, you will see a component. I think it's part of your kit, part of your mini lab kit. You have an IC. This is an IC, integrated circuit, which is op-amp. And it has a lot of pins, like 8 pins, and each pin is acting for a purpose. For example, V positive and V negative are the supply that you saw on the circuit. You have the output, you have the non-inverting input and the inverting input, okay? And these are the terminals that you will connect to the rest of the circuit to do your mini lab, okay? But these are all for practical and experiment purposes. What we need to understand for lecture part in order to be able to analyze circuits is a circuit symbol. So this is the first time that you're seeing a circuit symbol with 3 terminals, actually, okay? So this is an op-amp. As you can see, you have V out, which is the output terminal. You have 2 inputs, the V positive terminal, which is connected to the positive sign inside the op-amp, which is called the non-inverting input, and you have V negative, which is the inverting input. And I'm guessing those names are making sense to you. Inverting and non-inverting, negative and positive. Okay? What are the other labels on this symbol? So you see I positive, which is obvious. It's the current entering the op-amp from the positive input terminal, and I negative is the current entering from the inverting input. And you have I out. Now, next thing is that if you remember the concept of equivalent resistance, you remember, for example, we separated 2 nodes or 2 terminals on your circuit, and for example, I ask you to find the equivalent resistance from those 2 terminals, right? Now, if those 2 terminals are the input of your circuit, instead of calling it equivalent resistance or Thevenin resistance, we usually call it input resistance, for obvious reason. The 2 terminals that you are measuring the equivalent resistance are actually your input. Do you see? The V positive and V negative are your 2 inputs. If you solve the Thevenin circuit, or if you connect your multimeter across these terminals, you will measure the input resistance of an op-amp, okay? Why have I written it's equal to infinity? Because of the internal circuitry of this guy. If you measure the input resistance of an op-amp by connecting a multimeter or doing a circuit analysis, you will see that the input resistance is very high, in the order of mega ohm, okay? So because in this course we are considering an ideal op-amp, which means a very simplified version of op-amp. Instead of assuming that it's in mega ohm range, we will consider it to be infinite, okay? So the input resistance is infinite. Also, the output resistance, in a similar way, the output resistance is the resistance that is measured when the two terminals are at your output. Now you might be wondering, but you only have one output terminal. Where is the other one? Whenever you have a voltage labeled on your circuit, there must be a reference. So the other terminal is ground, okay? So when I'm saying V out is the voltage at that point, it's measured with respect to ground, okay? So R out is equal to 0, actually, based on the internal circuitry of the op-amp, okay? These are all points that could be a question from the conceptual part of your third exam. Okay, but what about circuit analysis? Now, there are three very important rules in analyzing op-amp circuits. The first one, there is no current going into the input terminals, both of them. I positive and I negative, the currents that going into the terminals of the op-amp are 0, okay? You might be asking why. First of all, this is an ideal assumption. Usually, these currents are very, very small, but we consider them to be 0. And the reason for that is that, look at the definition of input resistance, okay, which is infinite. Do you remember, based on the test voltage source, you remember that? If we applied a voltage source across the input terminal, 1 volt, and then find the current that's going into the terminal, and then divide the test voltage source by the current that's going into the terminal, it will give you the input resistance. Do you agree with that? Okay, if the voltage is 1 volt and the input resistance is infinite, how much current is going to the terminals? 0. That's the only number that makes sense, okay? Not exactly 0, but very, very small. So a direct result of infinite input resistance is actually the first rule. Okay. How about the second rule? The second rule states that the voltage at the positive terminal, or non-inverting terminal, and the voltage at the inverting terminal should be equal, which means V positive is equal to V negative. And the reason for that, so today we're talking about operational amplifiers. Okay, let's throw away the operational and just focus on amplifier. What does an amplifier do? Increase? It could increase the voltage, or if you want to stick to the word amplifier, we can say that it amplifies the input signal, right? Whatever your input signal is, it's going to amplify. For example, can you give me an example of an amplifier? What else? Mic and a speaker, okay? Microphone and a speaker. I mean, probably the most obvious one. So you talk to a microphone, the signal is picked up by the microphone, it's given to some amplifier, and then it's amplified, and then it's given as a signal to your speaker, and then the crowd will hear you. Now, a very important parameter of an amplifier is called voltage gain. Can you define that for me? Do you agree with him? For example, if we are focusing on voltage, let's say that the input voltage is 1 millivolt and the output voltage is 1 volt. What would you say the gain of this amplifier is? 1,000, right? Because it's amplifying the input by 1,000 and then it's giving it to the output, okay? So the gain is the output voltage divided by the input voltage. Now, in op amps, the input is defined, if you want to consider the input, as a differential input, which means the difference between the V positive and V negative. So this is how you define gain for op amps. V out divided by V positive minus V negative. So far, any problem? Now, the gain of op amps are designed to be very high. For example, in the order of 10 to the 5, okay, 100,000 or 200,000. So if the gain is very high, now let me ask you this question. Can V out be infinite or no? Can voltage of a circuit be infinite? No, because that's just not feasible. That's not practical. So let's focus on this equation one more time. The gain is very, very high. Let's say it's infinite. I mean, the gain is different. Gain is not a physical concept. Gain is a mathematical ratio. So the gain is very high. Again, not infinite, but in the order of 10 to the 5 or something. V out is some finite value, usually less than 2-3 volts, okay, for common purposes. Can you tell me what should be the denominator to make sense of this equation? Very close to 0. And if the denominator is very close to 0, what does it mean? The V positive and V negative are very close to each other, okay? Hence the second law, second rule of op amp. So V positive is equal to V negative, okay? Not exactly, but we are considering an ideal case, okay? These are the first two rules of op amp. If you look at the textbook of Circuits 1, there isn't a third rule. I just created this myself. And the reason for that is that for some reason, you tend to assume that the output current of the op amp is 0 or ignore it, and that's why I actually included that as a rule. I out is not necessarily 0, okay? You can never assume that the output current of an op amp is 0. Unlike the input current, which is 0, the output can be not 0, okay? I already talked about the input resistance being infinite and the output resistance being 0. And remember, these equations can be part of your conceptual questions on exam 3. Okay, we're done with the op amp concept. Now we're going to do some examples. And since your exam is coming up on Monday, I hope you know that, I'm going to do your web work for you. In the circuit below, IS is blah, R is blah. Find VO. We're going to start with Preston. I want you to apply the op amp rules to this. For a second, I thought you just came from a Formula One race. So what was the first rule of op amp? There's no current. So I positive is 0. I negative is 0. What is the second rule? Next. Okay, next. Chaz. You can look at your notes because it's today's lecture. You don't have to remember it. What is the second rule? V positive. V positive is equal to V negative. So is there any of these two voltages, V positive and V negative, that you know for sure? Andrew. Which one? Between V positive and V negative, is there one of them that you know for sure the value for?
Oh, V negative is grounded.
V negative is not grounded. V positive is grounded. How do you say V negative is grounded? Right? The bottom one is V positive, and it's connected to where? Ground. So do you agree with this? What does that tell you? That V negative must be 0 as well. Okay? Any problem? Good. Now, so can you tell me what's the voltage at this node? It's 0 volts, right? It's all one node. So let me write it here as this is V negative equal to 0 volts. And can you tell me what is the voltage at this node? That is VO. One more question. What is the current passing through this R? Next. Loeni. Luke. Much easier than that. Maybe you're right. You're trying to give me an expression for current, but I'm saying that the current passing through R is actually some very obvious value on the circuit. 0? IS. And can you give me a reason why? See, IS is coming up, then to the right, then it has 2 branches. How much of that goes to the op amp? 0. So all of it goes up to the resistor, okay? So that is IS. Now, what am I trying to find? VO. What do you suggest? What? Someone answer? Do you want me to redraw that part? Maybe that rings a bell. Look familiar? So, what should I write? 0 minus VO divided by IS is equal to R, which means VO is equal to negative R IS, and the values are R is 1.8 kilo ohm times IS is 5.6 milliamp, and it's equal to negative 10.08 volts. Any problem? So I want you to remember, whenever you see a circuit, including an op amp, before doing any circuit analysis, okay, you should do 2 things. The first one is to set the current going into the op amp equal to 0, set the voltage at the input terminals to be equal. Do we apply the third law that I just invented myself? No. You just be careful not to assume that, Okay? Okay, you have to be very careful. The third rule is actually a warning. Okay? So remember. Any question about the first problem? Any problem? No?
So it's I out in this case, IS. Or was it also zero?
Yes, exactly. If you so this current is actually IS, and it's not definitely it's not zero. Yes.
So in this situation, what does the op amp do if we could just have a resistor and a current supply in series and just have voltage drop of negative 10.08?
This op amp particularly, the only thing that it does, it gives you some problem to solve.
Okay.
Yeah, not necessarily a useful one. Yeah. But you will see very useful op amps in a minute. Okay. Any problem with this? Okay. Who's Hannah? Ready? Pass. Jesus. Start with the first rule.
Current.
The currents are zero. So I positive is equal to 0. I negative is also equal to 0. Read the second rule.
The voltages are equal, so V positive equals V negative.
Okay, whenever you want to talk about this rule, the voltage that are equal, go for the terminal that you're sure what the voltage is at. For example, if you look at the positive terminal, are we sure what voltage the positive terminal is connected to? Yes, because it's connected to a battery. So write the voltage at that terminal, V positive, is equal to 4 volts. What does that tell you based on the second rule? V negative should also be 4 volts. Everything else is exactly the same. So what is the voltage to the left of the resistor? 4 volts. What is the voltage to the right of the resistor? VO. What is the current passing through the resistor? IS. So this is what you can write. 4 minus VO divided by IS is equal to R, which means your VO is equal to 4 minus R IS, which is equal to 4 minus 2.4 kilo ohm. IS is 13.8 milliamps, and the answer is negative 29.12 volts. Any problem? Let's go for this one. Who was next? Yeah. Yes. I positive is 0. I negative is 0. Braylon. How are you? Next rule.
V1 or positive is
V positive is V1, which is 1.2. So,
V negative is
the same amount, right? V positive and V negative should be equal. V negative is 1.2, V positive is 1.2, okay? Pass. Cage. I'm going to ask you this question. What is the voltage here?
It should be
No.
V negative
V negative minus V2. Do you all agree with that? That's a battery. The positive terminal is 1.2. So if you write 1.2 minus the value of V2, which is 2.1, it will give you the blue dot. 1.2 minus 2.1 equal to negative 0.9 volts. Seth, what's this voltage?
here, negative 0.9. Pass.
Ethan,
Negative 0.9 volts.
why?
There's no current going through the resistor.
Do you agree with him? What's the voltage drop across a resistor? What's the equation for voltage drop across a resistor? Ohm's law, Ri. What's the current passing through Ri, R1? 0. Why? Because it's in the same loop as the negative terminal of the op amp and there is no current there. So the current passing through R1 is 0. So the voltage drop across it is 0. So it means that the black node is also negative 0.9 volts. What is VO then? Negative 0.9 volts. Did that make sense? Not? Okay. Gage.
I'm looking at my answer. Isn't the left side of V2 is positive?
Yes.
I think I'm thinking too much about it right now.
The left side should be higher because it's the positive terminal. Any problem? Okay. Who's next? Jonathan. Do the whole thing yourself.
I positive and negative is 0.
Let me see. I positive is 0. I negative is 0. What else?
Your V positive and your V negative are 0.
Sorry?
The V positive, V negative are 0 volts.
Based on what? Why?
Positive.
So start from here. V positive is 0. That makes the V negative to be 0. Okay? Then, you did 90% of the way. And unfortunately, since it is a multiple choice exam, if you leave it there, you get nothing.
So now you have to look at the current source.
No, why did you jump? What is the last piece of information that you derived?
Voltage.
Voltage at the negative terminal is 0. Try to find your way from there to the goal of the problem. So I'm going to move from the negative terminal to the output. See what happens there. So if I move from the negative terminal to the output, I'm passing over a resistor. And a resistor has a voltage drop. What's the voltage drop of the resistor? 0. Why? There's no current passing through that. If there is no current passing through the resistor plays the role of a wire. So can you tell me what is the voltage to the right of the resistor? Also 0. So what is VO? 0 volts. Remember, op amp is probably the easiest part of the third exam to get points. William, do the whole thing yourself.
So I'm positive and I'm negative is 0.
I positive is 0. I negative is 0. V positive is equal to 3 point. 3.1? 7. So V negative is also 3.7 volts. Okay? Remember what I told him. Start finding your way from the last piece of information that you found to the output. What's the voltage of the black point?
Wouldn't it just be V2 because it's the difference between V2 and ground?
Where is ground?
At the end of that was a resistor.
Here? But nothing to do with the black point. They are not connected anyway.
Is that the difference between V negative and V2?
Yes. So do you agree that this point is V negative minus V2, which is 3.7 minus 3.5 equal to 0.2 volts. So what is VO then? 0.2 volts. Any problem?
So the amplifier is not doing anything.
No, all of these circuits are just crap. Most of them. You will get to the good part. Any problem? Samuel, do the whole thing yourself. I positive is 0. I negative is 0. V positive is 0. So V negative is also 0. Okay, it's fine. Yes.
You just follow it all the way over, when it beats 0 again, because there's no current, so going through R3 is 0 volts, going over to VO, you have 0 volts.
Okay, you said there is no current going to R3?
What it looks like.
Why?
You have 0 current going there, and.
Where is there?
0.
There's a source. There's a voltage source. It's not a current source, but there's a source. So it's
Wouldn't it go straight to the ground? Well, no, it is parallel with resistors, it isn't just a wire.
first thing that you need to see here is that what happened to R2? shorted out. Do you see that? What's the bottom terminal of R2 connected to? Ground. The top, 0. So R2 is just gone. So the current that your voltage source is pushing passes through R1, and then where does it go? Through R3, because it cannot go inside the op-amp. Now, the previous circuits and examples were too easy for me and for teaching purposes, so I redraw the circuit for you. But this one, I think actually is a good starting point to tell you when it's better that you redraw the circuit and just get rid of the op-amp. Okay? This is how you do it. After you apply the first two rules and then simplify the circuit if there is something obvious. For example, here, the obvious thing was that R2 is being shorted out. Okay, now I'm trying to redraw the circuit. Positive, negative, Vs. Where does it go then? R1. Then I have R3. Then I have VO. And I'm going to put something here, 3 dots, which means VO, after VO, there are some things. For example, there is an RL, but I don't care about that. And you'll see why. You'll see that it's not going to affect my answer, okay? So there is one more thing that I need to put on this equivalent circuit, and that is the voltage between R1 and R3. What's the voltage here?
0 volt.
0 volt. Okay? Now, let's see. Let's look at this piece of circuit. What am I looking for? VO. Can I write a KCL at V negative? What should I write? 0 minus Vs divided by R1 plus 0 minus VO divided by R3 is equal to 0, right? That's the KCL. Plug in the values. What is Vs? 6.2. R1 is 3.7 kilo plus negative VO divided by R3 is 8.4 kilo. Equal to 0. Can I find VO from here? Yes. VO is negative 14.11. Okay? A couple of points. Where did we use the value for the load resistance RL? We didn't use it. Okay? Now, does it make sense why I actually didn't consider what's to the right of the circuit? I could have drawn it. I mean, it wouldn't change anything, right? I could have drawn RL there. But what I want you to tell you is that even if RL was open, even if you remove RL, the voltage is still equal to this value. Do you see where I'm going with that? That's why I don't care what's past VO. Even if you remove RL from this circuit and make VO the open, you see that there is still a path for current to go back into the op amp. Okay, so that's what creates the VO for you. And one more thing that I wanted to talk about, let me actually give you okay, this is an extra practice example. So find I out. How can I find it? 0.
We know VO, you should do the difference across RL.
We know VO, so based on Ohm's law, we can say how much current is passing through RL. Do we know how much current is coming from that branch? Yes, 0 minus VO divided by R3. Write a KCL at the output node. Write a KCL here. This is the output node, the black node. Okay? So KCL at VO. I out is equal to VO minus 0 divided by R3 plus VO divided by RL. You have all the values you can plug in and find it. Did that make sense? So in this specific example, let me ask you two questions. Does RL play any role in the value of VO? Does it play any role in the value of I out? Yes. Okay. So if they ask for VO, the output voltage, no. RL, we don't care about that. But if they specifically ask for I out, then RL play a role. Okay? Any problem? Now that we did the webboard problems, we're going to talk about famous and popular op-amp circuits. The first one is the non-inverting amplifier. I'm going to apply all the rules of op-amps and see what happens. So here, I positive is 0. I negative is 0. Do you agree that V positive is equal to V in? Whatever V in is. And so V negative should also be V in because of the second rule of op-amp. Now I'm going to write a KCL at V in. I'm going to write a KCL at V in. V in minus 0 divided by R1 plus V in minus V out divided by R2 is equal to 0. From here, I can write that V out over R2 is equal to Vn over R1 plus V in over R2. And from here, I can write V out is equal to R2 or V in R2 1 over R1 plus 1 over R2 If you do the common denominator for the inside the parentheses, it's R1 plus R2 divided by R1, R2, right? Then you cancel out these two, and you will get V in multiplied by 1 plus R2 over R1. And now I'm going to rewrite this like that. So this was your V out. I'm going to write V out over V in is equal to 1 plus R2 over R1. What did we call this parameter? It started with G. Gain, voltage gain. It's usually denoted by AV, voltage gain. And that's the gain of this amplifier. Which means that by designing the value of R1 and R2, you can actually design this to give you a specific value for gain. For example, if R2 is 10 times bigger than R1, your gain will be 11. Okay? And just so you know what it means to have gain, so let's just say that the red signal is your input. Okay? This is your input. And let's just say that the gain is equal to, for example, 2, suppose. If that is your input, what is your output? Let me do some magic. That is your output. Whatever your input is, double it, it will give you your output. When they are 0, they both 0. I mean, when input is 0, the output is also 0. When the input is maximum, the peak, the positive peak, the blue is also going to the positive peak. When it goes to negative peak, it goes to the negative peak. So if you're familiar with this function, that's a sine function, right? So the output is also a sine function, but the amplitude is doubled. That is called amplification, that is called gain. Any problem? Okay. So that is the non-inverting amplifier, one of the very useful amplifiers that are built based on operational amplifier or op-amps. Now, one thing, if you get this circuit on your third exam, I will talk about this when I'm doing the review of the third exam as well, but I want you to remember that. If you get this circuit for your third exam, the natural way is to do all the assumptions, write a KCL, 2-3 lines, and then find the gain or find the output voltage. But I suggest for those of you who are very comfortable with the rest of the material and think that you have some extra time, memorizing the circuit and the formula can save you a lot of time. Because usually the circuits that you get for op-amp are famous and popular ones that you've seen here. So if you can memorize it, it will save you some time. Okay? I'm not saying that's necessary or required, but you know the advantage. Okay, let's talk about inverting amplifier. Again, applying the op-amp rules. I positive is 0. I negative is 0. Voltage at the positive terminal is 0. so is the voltage at the negative terminal, 0 volt. Again, I'm going to write a KCL at V negative. So the current coming from the left is V in minus 0 divided by R1, and that current should go to the right. 0 minus V out divided by R2. And from here, I can write that V out is equal to negative R2 over R1 times V in. So the gain is equal to negative R2 over R1. Any problem with my calculation? Let me do that as well. Let me write the gain equation again because you're new to this concept. Okay? Now, that's the gain value. For example, if R2 is 10 times bigger than R1, you get a gain of negative 10. What does a gain of negative mean? So does it mean that the gain is not good? It's a bad gain, negative gain? It's just a phase change. If you don't know what phase is, wait a couple of lectures and we will talk about it. But it doesn't mean anything about the amplitude or amplification. It just means that the polarity is changing. Okay? So for example, if the red guy is here, and just let's assume that AV is equal to negative 1, which is called actually inverter. So what is the output? What does the output look like? See, the amplitude is the same, but there is a phase change. For example, if you have a heartbeat given to a inverting amplifier, it just be reversed across the horizontal line. You see that? That's called the inverter. Okay. Now it makes sense why we call this non-inverting amplifier. So non-inverting and inverting amplifier. The next one. This is I positive 0, I negative 0, V positive is 0, and this is 0 volts. Okay. I'm going to write KCL at the V negative. But before that, I'm going to talk about what's going on to the left of the circuit. So if you look at V3, it's pretty straightforward. The point that is shown by V3 is connected to a voltage source with the value of V3. Sometimes, just to make circuits more compact and more optimized in terms of representation, instead of doing that, we just put a circle at the point that we are interested in and write the value of the voltage beside. Look at V1 and V2. V1 and V2 are have the same behavior as V3, but they are more compact because we don't have to draw another voltage source and show it. So what I want you to understand here is that V1 and V2 are not open circuits. When I write V1 beside that, it means that there is some circuitry before that that is forcing that point to have a voltage of V1. We don't know how, we don't care. The only thing is that that voltage is V1 and the current is not 0 necessarily. Okay, it's not open. It may seem open, but it's not. Okay? Am I making sense to everyone? Okay, I'm going to write KCL at V negative. So what current is coming from the left? I have V1 minus 0 divided by R1 plus V2 minus 0 divided by R2 plus V3 minus 0 divided by R3. These are the currents coming from the left. And where does the current go? Through RF. So it should be equal to 0 minus V out divided by RF. Okay? Now, let's say that V out is equal to negative RF multiplied by V1 over R1 plus V2 over R2 plus V3 over R3, right? Yes. Okay, that's the end of my ability to write an equation for this example. And this is not very intuitive. So let's just make some assumption. Let's assume, suppose that R1 is equal to R2 is equal to R3 is equal to RF. And let's give all of them a common name of R. So V out is equal to negative R V1 over R plus V2 over R plus V3 over R. So V out is equal to negative V1 plus V2 plus V3. Can you tell me what this means? Is there anything interesting about the behavior of this circuit? Oh, well, the negative sign we don't care about because we already talked about it. It's just phase change. So if you forget the negative sign, is there anything interesting about this expression? Sorry? Exactly. So what do you suggest we call this circuit? Adder, right? Adding is one of the four principal operations, right? Now, do you understand where the name operational amplifier comes from? Because it actually can do operation on signals. This is one of them, adding. Okay? Any problem?
Is this the concept used when you have batteries in parallel series?
Batteries in parallel or series?
Like, let's say, TV or the batteries are using one down, one up.
No, that is just the internal circuitry because you want to combine them. That's the way, yeah. Okay, one thing, probably your question is about that. Guys, please think about this. V1, V2, and V3 are not necessarily batteries. They could be signal received from antenna from somewhere. Okay? Now imagine 3 antennas receive 3 signals, and you have a circuit that can combine them, that can add them. Okay? So don't think of it as battery. Think of a signal. Okay? The signal is any function that can carry information. It has a very general definition. So any signal that is coming from somewhere and you want to just add them together, you can do this. Yes?
Is this what they use in like power, like when they have like 3-phase motors, like generators, they use those combined voltages?
No.
Okay.
No. That's that has more to do with the physical concept that is involved inside the three-phase motors because of the way they are structured and because of the Faraday's law that happens. Okay, let's analyze this circuit. So this is I positive. This is I negative. Now, is there any of the terminal voltages, input voltages, that I know for sure? So I can base my second law of op amps on. Which one do you know for sure? Should I sit down? It's going to take a while because I'm not going to continue on until you tell me this. Could you please let me first sit down? Okay, what did you tell me?
Maybe the resistor like connected to the ground on this shorted out.
It's not. The bottom terminal is ground, but why do you say the top terminal is ground?
Well, it's on and like that gate line actually. Yeah. Although now looking, they're actually, I guess there's not, that's the only ground on this.
Idea. V positive is 0? It's not.
You could bump V2, using like V out, and that resistance. Like 1 and 2, or no, I could just, like, V out and V2, and use that, like ours.
Good Lord, it's fine. Is there something going on? That's your ringtone. Oh, okay. That's a very harsh alarm.
Does V2 in this case was not set up like that?
No? No.
Use V out to find V2.
How? No, but how? Okay, let me do this and see if that will get you anywhere. Do you agree that this part of the circuit can be modeled by the blue circuit? Is there anything different? I ignored the branch that's going to the positive terminal of the op amp because there's no current passing through that, right? So do you agree with this blue one? Now, can you tell me what is V positive? It's Friday. Give me some hope to continue to the lab as well. Huh? I've got a lab from 2 to 5. No. That's literally the only time that he actually paid attention to today's lecture. He was scared to death.
Why did you say yes to doing the lab?
Huh?
Why did you say yes to doing the lab?
I have to do the lab from 2 to 5. It's
Why did you say yes to doing it? Did you answer?
because I mean I will get some energy from you if you answer this. It is too damn easy. I know it's a Friday, but one half of V1. How? How in the world? V1 multiplied by R divided by R plus R. V1 over 2. That is called voltage division. So if this point is V1 over 2, what is the negative terminal? V1 over 2. So let's redraw the circuit from the top side. V2 is connected to R. Where should I go after that? I'm trying to redraw the circuit. Yes, to the other R resistor, and then finally I will get to V out. Remember, I don't care what's after V out, and I don't consider the circuit to be open, because if you remember, the output current is not 0. So there is one more thing that I need to put on this equivalent circuit, and if I don't, I cannot solve the problem. What is that? The voltage between the two R resistors is equal to V1 over 2. You could have done it just on the circuit as well. I mean, just by writing KCL, okay? So KCL at V negative V1 over 2 minus V2 divided by R plus V1 over 2 minus V out divided by R is equal to 0, right? Just a KCL. Get rid of R, multiply both sides by R, and it will give you V1 over 2 minus V2 plus V1 over 2 is equal to V out. I took V out to the other side. And V out is equal to surprise, huh? What is it doing? Subtract or differencing amplifier. Okay? Please do your in-class assignment, and I have to leave at 1:30. There's a workshop that I want to attend.